So friends, welcome to our second session on light. The second session on light is going to focus on refraction. If you are interested on reflection, you can see the previous video on reflection. Today we're going to talk about refraction, this particular video. We're going to do a quick recap of reflection and then we're going to see refraction. So in this particular session, we're going to cover about refraction, which is we're going to see refractive index with respect to glass. Then we're going to see how Snell's law is used to explain the bending of light, which is the refraction. Then we're going to study how light behaves with lenses, which is convex lens and concave lenses. We're going to see the various sign conventions and ray rules. Then we're going to see the image formation using the ray rules and then the formulas. So this we have seen in the previous session. I'm not going to take much time here. If you're interested, you can please see the previous video on reflection, which talks about mirrors, the ray rules of the mirrors, also the sign convention, the formulas, the image formation. It gives an animated view of how the images are formed for concave and convex mirrors. And then its application as well. And finally, the formulas we have seen in the mirror. So today we're going to see about refraction. So what is refraction? When we talk about refraction, refraction is the bending of light when it passes from one medium to another medium. एक medium से दूसरे medium जब जाती है, that time light bends. It bends. You can see my shot on how the pen appears bent in water. The pen actually appears broken in water. You can see the shot, which explains refraction in a very illustrative manner. Okay, here in this particular case, we have a glass, and glass is denser. Glass is denser, optically denser than air. Hence, air is the rarer medium. Glass is the optically denser medium than air. So when air travels, when light travels, मैं क्या बोल रहा है? Air travels. Air also travels. Light also travels. In this particular case, we are going to see about light. So when light travels, which is the yellow line here, and it hits at an angle I, which is the incident angle, then it bends. It bends in such a way that instead of going along the yellow line here, let me take a highlighter. Instead of going along the yellow line, see the yellow line here, instead of going along this line, it doesn't go in this line, but it goes along the red line. That means the light has actually bent, and it has bent towards the normal when it's going from rarer to denser. Now, when it's going from denser to rarer medium, when it is going from denser to rarer medium, then what happens? That time, the ray of light bends away from the normal. The ray of light, instead of going along the red line, dotted red line, it goes away from the normal. This is a very important topic. You need to imagine how the ray of light moves. This question comes during the board exam as well. So be very careful. So the laws of refraction state that when the ray of light goes from rarer to denser medium, then the light bends towards the normal. The second rule states that when it goes from denser to rarer, then it bends away from the normal. Rarer to denser towards, and denser to rarer away. So now let us see about Snell's law. How Snell's law uses to express how light passes from one medium to another. Snell's law is used to express how light travels from one medium to other. So basically you have the first medium's refractive index multiplied by the angle of incidence on the first medium, the surface of the first medium with the second medium, and the refractive index of the second medium with the angle of refraction. So now if you know the angle of incidence and you know the refractive index of both the materials, then you can calculate angle of refraction using Snell's law. Or many other cases, if the other three are given, you can find the fourth. Okay, refractive index of few common mediums are already known. For example, for air or vacuum, there is a slight difference. For vacuum, it is 1. For air, it is 1.003 or around 6, 006. Okay. And for glass, it is 1.33. Like that, for other mediums also, you need to remember the refractive index. I is the angle of incidence measured from the normal. R is the angle of refraction measured again from the normal. The key point to remember here, if you want to study in more depth, you can please let me know. Here, when the angle of incidence exceeds the critical angle, that time total internal refraction happens. Total internal reflection happens instead of refraction. Refraction doesn't happen when the angle of incidence exceeds the critical angle. That means instead of light actually bending inwards, it will reflect. It will reflect away. That means if you take a slab of glass here and the angle of incidence is such that it exceeds, angle of incidence is exceeding the critical angle of incidence, then what will happen? The ray of light, instead of bending, it will not bend, but it will initially, when it is equal to the critical angle, it will graze. It will graze. Then after that, it will reflect back. This is about critical angle. Now, how can Snell's law be expressed? Can it be expressed in any other way? So Snell's law can also be expressed directly in terms of speed of light in different medium. That means sine of the angle of incidence divided by sine angle of refraction is equal to the speed of light in first medium divided by speed of light in the second medium, equal to the refractive index of the second medium divided by the refractive index of the first medium. Right? That means here you see the inverse proportionality of refractive index with respect to speed of light. That means refractive index of a medium is inversely proportional to the speed of light in its own medium. Right? That is Snell's law expressed in terms of the speed of light and refractive index. So now that we have known Snell's law, let us see what kinds of lenses we need to study in this particular topic in our session. We're going to cover about spherical mirrors, spherical lenses. Spherical mirrors already done. And today's session is about spherical lenses. We're going to see shapes and sign convention. Now, when we talk about concave lens, it is bulging. It is bulging on a side, like a bulging belly. And this is a light fit object. Convex lens is a fit body. And concave lens is a bulging body. Mota tummy. And under wala tummy is convex lens. So here you have various terms which you need to remember. This is the optical center. O is the optical center. You can see in white here. This is to be ignored. Don't consider this. This is the secondary focus. This is the primary focus. And then you have 2f2, which is double of the focal length of the lens. And then you have 2f1, which is on the left-hand side. Similarly, for convex lens also, you have the optical center and you have primary and the secondary focus. So now the object is always kept on the left-hand side for convenience. Right? You can place it on the right-hand side, nobody stops. But for all practical purposes, we place it on the left-hand side. And all distances are measured from the optical center. We measure all distances from the optical center. That means we walk from here. From optical center, we either go right, or from optical center, we can go left. And if the object is on the left-hand side, that means all distances measured from the optical center towards the object on the left is actually going to be negative. And this side is going to be positive. So hence you can see the green indicator for positive and red for negative. For convex lens, the same thing, because the incident ray of light is coming from the object on the left towards the right. Hence, this side is negative. That means measuring from the optical center this side towards the right, towards the left is negative. And then towards the right, it is positive. Same rule. Along the incident ray is positive. Again, the incident ray, when you're measuring from the optical center, it is negative. Right? Height of the object, if it is above the principal axis, if it is this way, above, let me use green. Others will get confused. Let me erase this. Let me erase this, others will get confused. Take a pen, green, green, okay. Above the principal axis is positive. And below the principal axis, as you see in the red, it is negative. Negative this side and positive this side. Okay. These are the rules which you need to remember. One is about the distance and other is about the height and the location of the object. Just quick recap. Object is placed on the left, right? And all the distances are measured from the optical center for lenses and pole for mirrors. From the optical center, if you move along the incident ray, it is positive. Again, the incident ray measurements are negative. So now we'll see the ray rule. There are 3 ray rules for lenses. For concave or convex lens, there are just 3 ray rules. The first ray rule, if it is parallel to the principal axis on the left, then it goes towards the focus. It converges towards the focus. And the ray of light goes through the focus, then it emerges parallel. If the ray of light goes through the optical center, then it goes undeviated through the optical center. Remember, this is there is no reflection here, that is refraction. So in this particular case, when it goes through the optical center, it just goes straight, undeviated. For concave lens, this is convex. I'll write it down here. This is convex lens and this is concave. We have already seen how to identify convex and concave lens in a few minutes ago. Or you can just, rewind backward and then see forward. The ray of light, if the ray of light is coming parallel, then it will diverge in case of concave lens. It diverges, the red ray. It will appear as if it is diverging from the focus. The second rule, if it appears to pass to the focus, then again here also it will diverge, but it will diverge parallel to the principal axis. And here it goes undeviated. That is the third rule. Now the image formation cases for convex lens. We are going to use the rules what we studied to see how the images are formed, right? So the first image formation, see the first image formation here, when the object is at infinity. When the object is at infinity, the rays come parallel and they converge to the focus. They converge at the focus, that is at f2. The second image formation, when the object is at a finite distance to 2f1. When the object is at a finite distance from 2f1, let me take a laser pointer at 2f1, right? At a finite distance. That time the ray of light comes, one parallel and one going to the optical center, so that we can see where they intersect, right? The final emerging rays. They emerge, optical center wala to goes undeviated, there is no reflection or reflection. So that the second ray will actually bend towards the focus. So hence the image is formed between f2 and 2f2, right? And the image is real, it is diminished, and it is inverted. It is real, diminished, and inverted. Now third rule. Third rule is when the object is at 2f1. When the object is 2f1, again we use the image formation rule. One parallel ray and one to the optical center. Simple rule, right? We have this one parallel, one to the optical center. Now how they will actually meet? We have to see how they reflect or refract, right? So this ray parallel will actually refract. The other ray will actually go straight undeviated So the image is formed at 2f2. You can imagine this 2f1 or 2f2 like the center of curvature of a mirror. You can relate it likewise. Here the image is real. It is same size and inverted. The third rule, when the image is between 2f1 and f1, then when the object is between 2f1 and f1 here, then the image is formed beyond 2f2 here, right? The image is formed beyond 2f2. It is real, it is magnified this time, and it is inverted. Now when the image is at f1 itself, and again we need two rules, two rays. And then where do they meet? Oh, at infinity. Here they meet at infinity. Somewhere in infinity, they will meet. It will be a real image. It will be a magnified image and inverted, highly magnified here. It will be highly magnified here. And the final rule, the final image formation case is when the object is between optical center and f1. When the object is between optical center and f1, then again two rules, two rays. And here we can see that the rays are actually diverging. So they will appear to meet behind the lens on the same side of the object. So it will be a virtual image this time. It will be a magnified image and it will be an erect image. This is for convex lens. Here we have 6 image formation cases. Now for concave lens, very simple, just two cases. The first case is when the object is at infinity, and the rays will diverge. It will diverge away this way, and it will appear to meet on the same side of the object. It is at f1. Second rule, if it is somewhere between optical center, it is somewhere between optical center and at infinity. If the object is between optical center and somewhere at infinity, then again two rules. It will diverge again. The image will be formed on the same side. It will be virtual this time. It will be diminished and erect. So concave, as you can see, always virtual, always diminished, and always erect. Remember, for concave, I said mirrors earlier. It is actually lens. For concave lens, always virtual, diminished, and erect. Virtual, diminished, and erect. The image is formed on the same side of the object. So this is a tabular representation. I have denoted 2f2. You can imagine it that as the center of curvature itself. You can just imagine it in your mind so that you can remember it. Okay. So these are the tabular representation. This is for convex. It's self-explanatory. This is for concave. Is for concave. So when I put this arrows here, it means between infinity and 2f1. That time the image is formed between f2 and 2f2. This is where the image is formed. Or you can refer the image diagrams itself. They are more simplistic to understand. Right. So let me move forward. Lens formulas. There are two very simple lens formulas. One is the lens formula itself, and the other is related to magnification. 1 by f, you have to remember the negative sign in between. For lenses, we use negative sign in between. And for magnification, we have the positive sign here. Okay. For mirrors, we use negative for magnification, and we use positive sign for the mirror formula. Okay. It is 1 by focal length is equal to 1 by image distance minus 1 by object distance. And magnification is height of image divided by height of object, is also represented with distance of the image with respect to divided by the object distance. So this is a final recap of everything what we have done, reflection and refraction, full in just this particular few minutes. Light, we studied about light. We have seen the properties of light. It's an electromagnetic wave. It is a speed is about 3 into 10 raised to power of 8 meter per second. And then we have studied reflection and refraction. And in the reflection, we have seen how it behaves with mirrors. Mirrors, we have seen plane, concave, and convex. Then we have seen the laws of reflection. Angle I, angle of incidence is equal to angle of reflection, and focal length is half of the radius. Then we have seen the rules. If it is parallel, then it goes to focus. If it is true focus, it will go parallel. If it is true center, it will go straight backwards along the center only. And pole means it will come back, reflect back against the pole. Then we have seen the image formation rules. We have seen when the object is at infinity, what happens when the object is between infinity and center. If it is at center, as the object, in case of a concave mirror, as the object moves from left to right, then the image moves from right to left. It moves like this it moves. Object, image, object, image. And after the center, at the center is the same size. Okay. When they cross the center, the image will get magnified. Right? That's how you need to remember. For convex, it is always a diminished image and erect. We have seen that. We have seen the mirror formulas. We have seen positive here and then negative for magnification. Then we have seen for refraction. For refraction, we have taken glass. Then we have seen behavior with lenses. And then we have seen the rules for lenses. Parallel means focus, focus to parallel, optical center to optical center. We have seen convex lens image formation. Convex lens image formation is very similar to concave mirror. You can represent, for convenience sake, that center of curvature is nothing but 2f. Okay, 2f1 or a 2f2. You have to imagine it as the center of the sphere. Okay. For concave lens, it is similar to convex mirror. Those are the rules, very similar rules. That the image, in case of a mirror, the image will form due to reflection. It will come on the same side. And due to refraction, the image will come on the other side of the object. Then we have seen the lens formula. These are the two formulas which we have seen. Then for glass, what we have seen Snell's law. We have seen these two equations. One with respect to refractive index and other with respect to speed of light. And then we have seen finally for mirrors and lenses, we have seen sign convention. That means measurements are taken from pole for mirrors and from optical center for lenses. Measuring against the incident ray is negative. Measuring along the incident ray is positive. Height from principal axis is positive. And height below the principal axis is negative. This is all about today's session. Please watch both the videos, and then subsequent video we are going to solve formulas using the equation. Thanks for watching, and please subscribe if you have liked the video.